Hello everyone and welcome. Today we're going to talk about a family of molecules that is, well, absolutely central to pharmacology. They are behind some of the most common things we see in our clinics every single day. So let's get right into it. This is a very important topic.
So have you ever really thought about it? What connects the pain from an injury, a running fever, or that scary feeling of an asthma attack? On the surface, they seem like totally different problems, right? But believe it or not, deep down, they are all being directed by the same group of powerful chemical messengers in our body.
And the head of this family, the grandfather molecule if you will, where this whole story begins, is this one, arachidonic acid. Now normally it's just sitting quietly, locked away inside our cell membranes. But the moment there's an injury or some inflammation, it gets released. And that, my friends, is when all the drama starts.
Now here's where it gets really interesting. Once this arachidonic acid is set free, it doesn't just do one thing. No, it becomes the starting material for two totally separate production lines inside our cells. You can think of it like a major fork in the road.
And these two roads, these pathways, are named after the main enzyme in charge. First you have the cyclooxygenase or COX pathway. This one makes prostaglandins and thromboxanes. And the second one is the lipooxygenase or LOX pathway, which gives us the leukotrienes. Just remember these two names, COX and LOX. The entire story revolves around them.
All right, so let's first meet the kids from the COX factory, the prostaglandins and thromboxanes. What's so fascinating about them is that they often have completely opposite effects on the body. They're like two brothers in a family who are always arguing, but you know what? Their balance is absolutely critical for our health.
Let me give you a classic example. On one side, we have thromboxane A2. It's made by our platelets, and its main job is to make platelets stick together, to aggregate. This is super important for forming a blood clot when you get a cut. But then on the other side, the walls of our blood vessels are making prostacyclin, or PGI2, which does the exact opposite. It actively stops platelets from clumping together. So you see the beautiful balance here? Inside our healthy blood vessels, prostacyclin is the boss, keeping the blood flowing nice and smooth. But at the site of an injury, thromboxane takes charge to plug the leak. It's a perfect system, really.
Now let's look at another one of their roles. In the stomach, prostaglandins are absolute heroes. They are like the protectors, telling the stomach lining to make more mucus and bicarbonate and to increase blood flow. This whole thing creates a strong shield against our own stomach acid. So what happens when you take an NSAID, like aspirin? Well, it blocks these prostaglandins, and suddenly that protective shield is gone and the acid can attack the stomach wall, leading to ulcers. Remember this. This is a classic Viva question.
And what about pain? It's a common misconception that prostaglandins directly cause pain. They don't. Instead, look here at the nerve endings. What prostaglandins do during inflammation is they sensitize these nerves. They make them hyperreactive. So a small touch that normally wouldn't hurt now feels incredibly painful. Prostaglandins aren't the fire, they're the kerosene that makes the fire burn much, much hotter.
And fever? Well, when you get an infection, your body releases these things called pyrogens. They travel all the way up to the brain's thermostat, the hypothalamus. And there, they signal for the production of prostaglandin E2, PGE2. This PGE2 basically just goes to the thermostat and cranks up the setting. And just like that, you've got a fever. Simple, right?
Okay, so that was the COX family. Now let's jump over to that other road, the LOX pathway. It's time to meet its children, the leukotrienes, and these guys are the main culprits when it comes to allergies and asthma.
The key players here are leukotrienes C4 and D4. See, a long time ago, scientists found some substance that was released during bad allergic reactions. It caused a very slow but very strong muscle contraction. So they named it the slow-reacting substance of anaphylaxis, or SRSA. Much later, they figured out that this SRSA was actually a mix of these very leukotrienes. And what do? Well, they do everything you don't want to happen during an asthma attack. They are incredibly powerful bronchoconstrictors, way more potent than even histamine. They make the airways produce more sticky mucus, which makes it even harder to breathe, and they cause the airway walls to swell up. In short, these are the key villains in allergic asthma.
So, now that we know the family and all the trouble they can cause, we get to the most important part, the pharmacology. How do we control them? How do our drugs interfere with these pathways?
Let's start with the most famous drug of all, aspirin. The way it works is actually quite brilliant. Aspirin finds the COX enzyme and it chemically changes it through a process called acetylation. Now, this isn't a temporary block, it's irreversible. The enzyme is permanently knocked out.
The cell has to make a whole new enzyme from scratch to start production again. This is why even a small dose of aspirin has such a long-lasting effect.
But what if you want to block everything? That's where steroids come in. They are the big guns. Instead of just blocking one pathway like COX, they go upstream. They stop the release of the parent molecule, arachidonic acid itself. So if there's no arachidonic acid, there's no raw material for either the COX or the LOX factory. Production of everything, prostaglandins, thromboxanes, and leukotrienes just stops.
And this table here summarizes it perfectly. Look, NSAIDs like aspirin target the COX enzyme, so they only block one branch of the family. Steroids, on the other hand, target an enzyme called phospholipase A2, the one that releases arachidonic acid, so they shut down both branches. This is exactly why steroids are such powerful anti-inflammatory drugs.
But wait, the story isn't just about blocking these molecules. Here comes the twist. In a beautiful piece of pharmacology, we have also figured out how to copy them and use them as medicines. We have turned these troublemakers into powerful tools for treatment.
And just look at the applications, they're incredible. We use synthetic versions or analogs of prostaglandins for so many things. We use them in obstetrics to induce labor, we use them to protect the stomach. They are a first-line therapy for glaucoma. In newborn babies with certain heart defects, they can be life-saving by keeping a crucial blood vessel open. The list just goes on and on.
And this slide just gives you an idea of some of the names you'll see. On one side, you have the natural prostaglandins, our body makes, and on the other, you have the synthetic drugs we've engineered in the lab. It's a perfect example of what we do in pharmacology. We take a signal from nature and we modify it to create a powerful medicine.
So this is the main thing to take away today. This one family of molecules is responsible for causing pain, fever, and inflammation. But by understanding them, we've developed drugs that relieve those exact same things. And we've even made copies of them to treat a whole bunch of other diseases. It's a two-sided coin.
It's really a fascinating duality, isn't it? We've learned to stop their production, and we've learned to make our own versions to use as drugs. So the question for the future is, what's next? How can we get even smarter? Can we make drugs that are more specific, that give us all the benefits with even fewer side effects? That's the challenge ahead, and a great reminder of the complex chemical dance happening inside us all the time. Thank you for listening.